In principle, now you see my pad.
Yeah, we can see.
Okay. Very good. So last time we saw that how to prove a Carleman estimate in a quite general setting for the Laplace operator based on some condition on the weight functions. And then I've explained that these conditions can always be satisfied no matter of the geometric conditions. And so, for instance, you have this kind of unique continuation property that if you solve some kind of elliptic equation with rather general coefficients, and if it vanishes somewhere, then it vanishes everywhere. So in fact, there are a lot of results like this in the literature. So I will mainly dedicate this lecture on unique continuation results. And their quantification. And in particular, known as Lambda, which is the following. So if you have a solution U, let's say in L infinity of Rd such that the Laplacian of U is less than U and the limit of U of X exponential x to the power epsilon as x goes to infinity equals to 0, then U vanishes identically. Okay, so somehow this is saying that, so one important condition is this one, which is smallness at infinity, right? And more or less you should think of it as U of X smaller than a constant exponential minus x 1 plus epsilon as x goes to infinity, right? It's more or less equivalent. You see here, it means somehow that U vanishes in a neighborhood of modulus of x equal to infinity, and what matters is the rate. What matters is the rate of this cancellation. And so let me tell you from the beginning that we only have partial results on this Landis conjecture. Only partial results. On this Landis conjecture, and this is what I'm going to discuss today. Okay, so let me maybe start. So here you see everything, right? So you see you have, so Laplacian U smaller than U in Rd. So this means that if you set means that if let's say v of x equals to Laplacian u of x divided by u of x. This is something which belongs to L infinity in Rd. In fact, of L infinity norm bounded by 1. Okay, and you have minus Laplacian u plus vu equal to 0 in Rd, right? So this is very much related to the behavior of solution of an elliptic equation with a potential. Okay. So, and in fact, sometimes I would simply say that I will speak about a potential even for u which satisfies only Laplacian u smaller than u, and the meaning is that the potential is Laplacian u divided by ux. Okay? So, what are the results? So, by the way, Landis conjecture, I think it has been, so let me check the dates. So I think it was in the late 60s. But it was published in English, at least in a joint work with Kondratiev, I believe, in the 88. Okay, and so and it still resists, right? So it has more or less 50 years, and still we only have partial results. So that's a bit of a surprise, right? Okay, so what are the results? So the first result, probably the most striking one, is the one by Meshkov in 91, which says that so there are two parts. One is a negative part. There exists a solution or a function u, let's say a function u in L infinity of Rd with values in C such that Laplacian u is less than u in Rd, u of x is less than, let me check, I think it's exponential minus c x to the power 4/3, such that for all x in Rd. So I just realized that here I didn't say what was epsilon, right? But epsilon, of course, is positive and it's small. Okay. So I didn't say, I just realized it. So somehow the critical limit should be epsilon equal to 0. Yeah, maybe I should say that. For epsilon equal to 0, we have a typical solution, which is u of x exponential minus c modulus of x, okay, which is of course something which decays like exponential minus modulus of x at infinity, right? You may say that it is not smooth, so maybe it does not satisfy the condition that Laplacian of u is smaller than u. So it satisfies Laplacian of u smaller than u outside of the ball. Okay, so the only problem you may have is close to x equal to 0. So here you can simply take a cutoff. So here it's a smooth cutoff function equal to 1 away from 0. Okay, so somehow this is the critical function. And so it is expected that really the limit should be at exponential minus x. So if you want to have something which is really, oh, sorry, we'll go back here. So if you want to have something which decays more faster than that and satisfies Laplacian of u smaller than u, then it should be 0. So it should be really the critical thing. Okay, so Meshkov disproved that. And he proved that there exists a function u, complex value, such that you have Laplacian of u smaller than u, you have u of x less than exponential minus c modulus of x to the power 4/3, and u, which is non-identically 0. Okay? So this came as a surprise, and really, there's one point here which should be mentioned, is that u is complex valued. So maybe I didn't say, but for in Meshkov, I think the result is for d larger than 2. Okay. So this is an explicit construction, but u is complex valued. So the question is, what happens if u is real valued? We still have such counterexample. To land this conjecture. And so far, the answer is that we do not have any counterexample for u real valued. Okay, so this is still an open problem. And in Meshkov, there was also a positive result. Saying that this decay as exponential minus x to the power 4/3 is really the critical one. So let me move it. So it's a theorem due to Meshkov again, 91. If u satisfies Laplacian of u less than u in Rd, that the limit, and there exists epsilon positive such that the limit of u of x exponential x to the power 4/3 plus epsilon equals to 0 as x goes to infinity, then u vanishes everywhere in R. Okay, so this means that really this exponential x to the power 4/3 seems to be the critical thing, at least for possibly complex valued functions u. Okay, so let me give you the proof. So in fact, we did everything to get this proof. So let me mention it. So let u in an infinity of Rd satisfying the assumptions. So then there exists potential V in L infinity over D with the norm of V L infinity smaller than 1, such that minus Laplacian U plus VU equal to 0 in omega, in RD. And then what I want to use is Carleman estimates. But in Carleman estimates, you remember probably that I was always assuming that I was working in a smooth bounded domain. And here I am in RD. And also I gave you the dependence of the constants when the potential was large. So it seems that the link is perhaps not so clear. So what we do is, in fact, quite simple. It's simply a rescaling argument. So you set for R positive large, you set UR of X equals to U of Rx for X in the ball of RD of size 2. So let's do that. Then what? Then UR satisfies some PDE, right? And then, so it's only a computation, you'll get that minus Laplacian of UR plus VR of UR equal to 0 in the ball of size 2 with VR of X equals to, so let me check, R2 V of Rx. Okay, so in particular, what is very nice is that the norm of VR in L infinity, this is simply, this is less than R squared. This is on the safe side. Okay, but then you see this UR, so it satisfies an elliptic PDE, but you do not have boundary condition. Okay, so what you are going to do is to introduce some cutoff. So let eta be a smooth cutoff function. Let's say that eta equals to 1 in the ball of radius 1 and vanishes equals to 0 in, let's say, the ball of size 2 minus the ball of size 3 half. Okay, so then you simply set VR of X equals to UR of X times eta of X in B2. So, okay, it's only a small play, and what you get at the end is that minus Laplacian of VR plus VR is, so simply, in fact, the commutator of eta, of the multiplication by eta and of the Laplacian, right? So it's minus Laplacian commutator with eta applied to UR of X. So if you do not like this notation, it should be minus 2 gradient of eta gradient of UR minus Laplacian of eta times UR. Okay, so what matters with that is, so this is localized. in the ball of size 2 minus the ball of size 1. But there, remember we had that UR of X is U of Rx. So this one, in fact, this is bounded by a constant times exponential minus modulus of minus R to the power 4/3 plus epsilon. And then by elliptic regularity, by local elliptic estimates, you get the same thing. You get that gradient of UR of X is less than a constant times exponential minus R 4/3 plus epsilon in the ball, in the ring, in fact, ball of size 2 minus 1/7. Okay, so somehow VR satisfies your equation in B2. So let's try to sum up. We have that VR satisfies minus Laplacian VR plus some potential VR times VR equal to some source term in B2 minus B1. We have VR which vanishes on the boundary of the ball of size 2 because we simply have introduced some cutoff. We have that the norm of VR, the norm of the potential in B2, this is less than R squared. And we have that the norm of FR in, let's say, L infinity is bounded by C exponential minus R 4/3 plus epsilon. Okay, so what will come next is an application of Carleman estimate. So we take omega equal to B2 minus B1. No, sorry, omega equals to B2. Small omega equals to B2 minus B1. Okay, then we have a weight function phi, and there exists a weight function phi. Such that there exists a constant C, such that for all S larger than 1, we should have S to the 3 times VR times VR exponential S phi in L2 of omega squared plus, do I need the rest? I don't need the rest, so I will just remove it. It's less than C times Laplacian VR exponential S phi L2 plus constant times VR, so there's a S to the 3 here, VR exponential S phi in L2 of small omega. Okay, so on Laplacian VR, you see this is, so remember the equation, it's VR. So, okay, I think it's a poor choice of notation, so I'm very sorry for that. So this capital V here is the potential, and small v is the function, right? So this is less than C times VR L infinity square in omega times VR exponential S3 L2 omega square plus constant S3, sorry, I forgot one term, plus constant times FR exponential S5 in L2 of omega plus the observation term S to the 3 VR exponential S5 L2 of omega squared. And then you see if, so this is the same argument as always, if S to the 3 is larger than the norm of VR and infinity squared, we can absorb that term here by the powers of S, right? So, of course, this can be done. So it's okay if S to the 3 is larger than R squared to the square, because the norm of VR is like R squared. So this is okay if S to the 3 is larger than R4. So meaning S larger than R to the power 4 third. So you choose S as S equal to some constant times R over 4 for C large enough. So then you get that S to the 3 VR exponential S5 in L2 of omega square is less than a constant times FR exponential S5 L2 of omega square plus constant S3 VR exponential S5 L2 omega square. And you see FR, I've told you that FR is smaller than exponential. So here it is. So FR is smaller than this, right? So I've put L infinity, but of course, I mean, you can get it in L2, possibly to the price of paying some polynomials in R, but this is nothing compared to the exponential, right? So this guy, the first guy, this is bounded like exponential S, let's say norm of 3 at infinity, times exponential minus C R to the power 4 over 3 plus epsilon. And for the second guy, so this is VR, localized on small omega. So this is like UR localized on small omega. Okay, remember that VR is UR times the cutoff, okay? And UR in small omega, this is less than exponential minus R to the power 4 over 3, right? So it's the same. Here you get constant exponential S5 exponential minus C R over 3, 4, 3 plus epsilon. Okay? And so, of course, on the left-hand side, you also have something here. So this guy is like, it is certainly larger than S to the 3. So S is large, so let's say that S is 1. And 5, let's say it's positive, right? So this is certainly larger than VR in L2 of omega squared, right? So you see, in fact, at the end, what you get is that the norm of U, so you then You then undo the change of variable, and what you get is that the normal view in L2 in the ball of size R to the square is less than a constant times exponential. So remember that S is like R to the power 4/3. And so you get something like that. And so, of course, this goes to 0 as R goes to infinity. And so you get that U vanishes in art. Okay, so you see the proof of this positive result. This is a direct consequence of Carleman estimates and the cost of the observation of the observability for an elliptic equation with respect to the potential. Okay. So then on Landy's conjecture, then back to Landy's conjecture, basically there was almost no result up to 2005, where there was a work by Bourgain and Koenig, 2005, which uses some kind of refined version of Landy's conjecture. Okay, but I don't want to discuss it, but which can also be proved using Carleman estimates. And then there was a renewed interest around Koenig and Wang. I think it was 2000. I never know the dates. Okay, so let's say 12, but I'm not sure. And then there was a very recent result by Logunov, Malinikova, Nadirashvili, and Nazarov, which to my knowledge is still unpublished, but which proves it in 2D. Okay. And almost simultaneously, there was a result by Sirakov and Souple. But in these results, they use some kind of positivity and some kind of maximum principle. Okay? So meaning that you should have some kind of sign condition on the potential. Okay, so I don't want to discuss it more. So Koenig and Wang in 2012 is about this refined version of Landy's conjecture. So you see, basically, we have the Landy's conjecture in 2D, and that's all. So otherwise, so I think Sarkov and Souple should be 2021 or 2, I don't know, between the preprint and the publication, but okay. So there were still some works, and this is still an open problem by many aspects. Okay. So I've told you, or maybe you know, that I'm more working in control theory. So in fact, I should tell you what was my motivation related to control theory. So the motivation comes, in fact, from an article by Fernandez-Cara and Roswa. I think it was in, well, I'm sorry about the dates. I'm always getting it wrong, but I think it was 2002. Okay. There they studied the controllability of the heat equation So let's say you have a smooth bounded domain. You are considering the semilinear heat equation. You got, so you get an initial condition. And the question is, so given similarity, okay, can you prove global null controllability in any time? Anytime, meaning for all t positive, for all y0 in, let's say, L infinity, which is a reasonable space when you are dealing with semilinear equation. Does there exist a u in L infinity, so 0t cross omega? So here this one is local, is a indicator function, right? So it's localizing in small omega, such that the solution y satisfies y at time t equal to 0. Okay, so this was the question asked in this article, and the answer was related to the behavior of f at infinity, right? So the answer was the following. So if, let me try to get it wrong. So if there exists p smaller than 3/2 such that f of s is a small o of s log p of s as s goes to infinity, then you get global null controllability in any time. So the answer is due to Fernandez-Cara in this way. And if you take fp of s as the integral from 0 to s of log p1 plus s tilde ds tilde, then there exist initial conditions y naught such that whatever u is, you get a blow-up. Okay, so not that, so for p, sorry, for p larger than 2, so fp of s, in fact, this is equivalent to modulus of s times log p of 1 plus s at infinity. Okay, so really you see there's a gap between this thing here and this thing here, p larger than 2. And the fact is that this is related to for the positive result, this is related to Carleman estimates. So in their work, they did that for using the Carleman estimates for the heat equation. And so I just want to tell you that, in fact, all the difficulties that are there for the heat equation, they also appear for the elliptic equation. And so there is a kind of toy problem to understand it that we discussed with Kevin Lebalch in a recent work, which is the following. So let us consider the elliptic problem minus Laplacian y plus f of y equal to f plus localized control u y on the boundary equals to 0. And the question is the following. So under which conditions on f can we guarantee, so f, small f is the semilinearity, right? On the semilinearity f, can we guarantee that for all f, so for all source term, there exists a control function u and a state y, solution of the equation. Okay, so this is some kind of optimal control problem. So there are some capital F for which there is no U, if in particular in the case in which a small f is negative, okay, which could yield to some kind of blow up on the parabolic side. And so this is really the analogous of what happens for the heat equation. And here we also have this result, which is, again, the analogous of the one by Fernandez-Cara and Joshua, is that if for some p larger than 3/2 minus Laplacian, so sorry, f of y, f of s is a small o of s log of p s as s goes to infinity, then for all f in L infinity, there exists uy, so u will be a control, so it is localized in small omega, and y will be the state, so satisfying minus Laplacian y plus fy equal to capital F plus u in omega, and y on the boundary equals to 0. So for the proof, so let me just give you the one inside. So the inside is exactly the same as the one in Fernandez-Cara and Joissois' work, right? So to simplify, assume that f of 0 equals to 0, and then given y hat, consider the control problem. For minus Laplacian y plus f of y hat divided by y hat times y equal to f omega if y on the boundary equals to 0. So somehow this term here defines q of y hat as a potential. Okay, so then you see that you should have some kind of control results where you get an estimate on y and an estimate on u, which would be bounded like exponential c norm of q of y hat at infinity for third, no, sorry, 2 over 3 times the norm of f. So I do not want to specify the norms, but in principle, you should have something like that. So probably here it should be L2, by the way, and here it's L2 omega. So just to be clear, for all Q, well, you can solve the problem without the control. Right? But the goal is to find the pair y and u, which minimize the quantity, the norm of y plus the norm of u, among all the solutions of the above problem. Okay? And once you have that, it's well, classical duality argument, let's say, which will tell you that you can find a control function u such that the state y satisfy this condition. So there exists u in L2 of omega such that you get this estimate. And so then let's say that you are in dimension d larger, less than 3. So you'll get that the norm of y L infinity of omega will be less than the norm of y in H2 of omega. So it will be less than c exponential c, the norm of q of y hat L infinity to third times the norm of f in L2. So what you want for your map, y hat gives y, you want it to send a bounded set to a bounded set. So what you are considering is this map, okay, so which takes y hat in L infinity and gives you some y in L infinity, and you want lambda to send, let's say, and what you want, sorry, is if y hat, do we have that the norm of y in L infinity is smaller than r. Okay, so this is typical in all these fixed point type arguments. You want to construct a fixed point map such that some map, okay, such that it sends a ball into a ball. Okay, so here the balls should be considered in L infinity. So if y hat is in L infinity is bounded by r, then what about the norm of q of y hat? Well, this guy, this is the norm of f of y hat divided by y hat, right? L infinity. Okay, so remember, I've told you f of s less than constant s log P of S for S large. So of course, if you remember that f of 0 is 0, it's easy to check that you can have this for all S in R. Okay? So then, the norm of f of y hat divided by y hat in L infinity, you see it would be bounded by a constant times log P of 2 plus norm of y hat infinity. Okay, so what? Remember what we got here, right? So we got here that the norm of y and infinity of omega is less than this. Right, so you see what you want, so it would be okay. But the norm of y and infinity in omega would be bounded by a constant, exponential constant, log of 2p over 3 of 2 plus r times the norm of f in L2. Okay, so in particular, you see that if 2p over 3 is smaller than 1, then the exists are large enough such that c exponential of c log 2p over 3 of 2 plus r times the norm of f in L2 is less than r. Okay, it's simply a matter of comparing the growth of in R. And so you have a map which maps a bounded set of L infinity into itself, and then you can end up with Chowdhury type argument. But okay, this is more or less classical. Okay, end of the proof by a fixed point argument. Okay, so I think that my time here is almost over. So I just want to mention some applications of Carleman estimates. Probably you saw some of them already, depending on your field of study, but it appears in many situations in inverse problems. So for instance, when you look at the uniqueness in the Calderon problem, in dimension larger than 3, there's a construction of what is called CGO solutions, so complex geometric optics solution. And here, this is really a case in which you need to track down how this construction depends on lower order terms. And so Carleman estimates are used. You may have also stability properties for the Cauchy problem for Laplace operator. So this is what we saw in the beginning of the lecture in the very specific geometric setting. But of course, it appears in many other places. In unique continuation, you have you have one property which is perhaps not so well known, which is what is called the strong unit continuation. Which is more or less the analogous of what you have in the context of holomorphic functions. So if you have Laplacian u plus vu plus, let's say, w gradient of u equals to 0. And so let's say this is in some ball, right? And u vanishes at infinite order in 0, then u vanishes everywhere in B. And so here I just maybe have to say what it means for u to vanish at infinite order at some point. It means that for all n in integer n, exists a constant Cn such that when you look at the integral of u of x of the ball of size r, this is smaller than Cn r to the n for all r small n. Okay, so this allows to define vanishing at infinite order even for L2 functions. So some functions which are in principle not infinity, right? So you see, this is a solution of an elliptic equation with potentials, which might be in L infinity or stuff like that. So it is not at all clear to define it very rigorously. So this is the rigorous definition. So also you have, of course, unit continuation of okay, so if minus Laplacian w equal to lambda w, and so let's say this is vanishing on the boundary, and w vanishes in omega, then w vanishes everywhere. Okay, which is something which is useful when you are doing stabilization, right? It's a kind of Otus test for the Laplace operator. Okay, not quantified, but this is useful in stabilization. Of course, you can do that for much more sophisticated operators like Stokes operators, for instance. So this is quite nice. And also you have what is called in general Lobo-Robiano spectral inequality, which I have no time to discuss here, but which is of course useful in the controllability properties. Wait. The null controllability, let's say, the heat equation. So I think I will stop here. So just to mention that it has a lot of applications, and somehow it's a kind of fundamental tool that, and I hope that I gave you some insights on it and how to use it. Well, thank you.
Thank you, Sylvain, for the nice talk. Now I ask the audience if they have a question they can ask. Also the online participants, if they have a question, they can write or they can ask Sylvain directly after unmuting them. Okay. So Sylvain, I have just one question regarding this problem you are telling about the parabolic one for the heat equation case. So if it is a heat equation case, in I consider the nonlinearity minus YQ in the right hand side. So it is stable.
Yes.
In that case, if I use a localized interior control, I know that the system will be not globally approximately controllable because of some obstruction phenomena.
In which case, again? So
Ut minus uxx.
Yes. So this one.
So here fy I choose as plus yq, so that when it will go to the right hand side, I will have minus yq.
Okay.
So you have localized control, and due to that, the barrier function, or if you use cutoff by localized control where there is no control is acting, due to that phenomena, you will not have global approximate controllability in a given time. Because there will be certain data which close to that you cannot reach. Like
Okay.
Fusikov
Yes.
kind of multiplier if you use. If you outside the control region, then there is due to of this nonlinearity and multiplier, then there will be certain data which you cannot reach.
Okay.
But the question is that one, so there will be certain ball depending on the time, all those things. But if you are inside that ball, can you get some kind of a controllability? I'm not saying about the local controllability in a small R. I'm saying about outside that R I cannot reach. Inside that radius of the ball, can I reach?
I don't know. Well, I have to look at your question more precisely. Like this, I'm not able to say.
Okay. Because this is with a like of we have seen for the when we study the approximate controllability for a heat and OD, or only if you heat, if you have a cubic nonlinearity with a minus sign in the right hand side, you will have this kind of obstruction phenomena.
Okay. Thank you.
Okay. Thank you, Sylvain. Okay, so maybe we can thank again Sylvain.